This is track 6, one more time. This is routing SIM cards with Karsten Nohl. The other talk has actually been moved to tomorrow, Thursday, at 15:30. So please welcome to stage Karsten Nohl.
Thank you very much. I'm a security researcher out of Berlin, where I run a hacking think tank. Our research mission is to find vulnerable cryptography in everyday use. And we've been doing this for a few years. We found applications on and on from 20, 30 years back that are still being used. And of course, they're using bad encryption. Now we thought we were done until we found this one more application. Maybe it's the last one that falls into our research. We never know. But I'm here to speak about SIM cards, the little computers in your phones, or in most everybody's phones. There's a few exceptions of older CDMA phones that don't use SIM cards. Everybody else uses a phone. GSMA says there's 7 billion in active use, growing every day. So these would be a very attractive hacker target. And we looked at how to hack them and found surprising things. SIM cards were originally meant as a way for the phone to be paired with the contract, so that the charges would be put on the right contract and that the calls would reach the right phone number. But they've been extended into all kinds of other directions since. With functions for very feature-limited phones, like storing an address book or storing text messages. These are the more known extensions of SIM cards, but also through custom Java code that can pretty much do anything, and that can be updated at any point in time. Popular uses here are roaming management. That is, when you touch down in a country that you haven't been before, your operator updates a list on your SIM card that says, I prefer this network over this other because I negotiated better rates. So it has to do with revenue optimization. Also, payment applications are found on SIM cards in the developing world a lot already. In Africa, predominantly, I take it. But it's also coming to the developed world in the form of NFC payment tokens. So when your phone becomes a credit card, that's facilitated through a software download onto the phone. Very popular in Japan, as I learned today already. It's coming here, any day now, but they've been saying that for years too. We find a bunch of different security mechanisms on the SIM card. It's a complex computing system, so it has to secure a whole range of different things. And let me first state what we're not going to cover today, just to make sure what the focus is. We're not discussing, how to break PIN numbers that used to lock SIM cards. In fact, the attacks I'm going to present, they were completely outside of the realm that's even protected by PIN numbers. So you can send those messages that we'll be using to cards where you don't even know the PIN number, or it has not been typed in. We're not going to get into authentication functions. What used to be SIM cloning some 8 years ago, COMP 128, some people may remember that. So that's a different type of research, and that abuses just one application of the SIM card. We want to go deeper, but not quite as deep as the smart card. So that's also something we're not going to discuss today. If you go back, I think 2 years ago, I gave a talk here with Karsten Nohl. There we show how to break a smart card. But who remembers the talk from back then? It was a somewhat elaborate process that took a couple of days in a lab. So maybe nothing you would do to your neighbor's SIM card just to break it. In fact, you would physically need to break it in order to break into it. So that's also not of concern. Instead, we want to focus on the management interfaces that network operators use to deploy or reconfigure Java applets on the SIM card. And we first want to look at the management interfaces for the communication of those Java downloads, and then look at what the Java applet is allowed and should not be allowed, can do anyway on the SIM card. Sounds good? Yeah? Okay. if there's any immediate question or any questions, raise your hand, right? I'll try to answer them as they come along, otherwise at the end. So we want to go into two deep dives here. One, to discuss how somebody would be able to deploy a malicious piece of software onto the SIM card, cracking some cryptographic keys with permissions to do that. And then we want to discuss what one can then do with that Java on the SIM card. This is all grounded in these management protocols I mentioned earlier that are meant for the operator to control the SIM card while after they already gave it to the customer. And the communication between the operator and the SIM card is all text messages, but of a certain type that is not actually displayed on the user phone, but instead directly forwarded onto the SIM card. So there's a header in every text message that defines its type, and certain types are supposed to be shown to the user, others go directly to the SIM card. And virtually every phone honors these flags. We found maybe one phone in the last 3 years that just ignores OTA entirely. And so to secure this communication, this critical communication that really can change a bunch of things on the SIM card, cryptographic signatures and or encryption are used. Signatures are much more popular than encryption, even though when you think about it, they're actually fulfilling the same purpose here. Both use a block cipher and counter mode, but somehow they like the signatures better than the encryption. Some operators use both. We'll see in the end that it makes a little difference, though. The SIM card is configured at manufacturing time or at initialization time with a number of keys. So it doesn't just have one key that somebody from the outside can speak to, but a whole number of keys. And these are, again, assigned to different applications. So it can have a number of applications, and for each of the applications, up to 16 keys. So it really allows business cases where, for instance, the operator has a spare application with a couple of keys on it and then sells that to, let's say, a bank, and they would then deploy the banking logic onto this part of the SIM card, not affecting anything else, though. So the SIM card knows which type of security it can speak in terms of algorithms, and also it knows whether, for instance, signatures and encryption are mandatory. Now, this slide already gives you a first idea of where this system may be vulnerable. Since not just the AES standard that we know from basically every internet application is an option, and the triple dash function that's was a quick fix to a cryptographic problem in the 80s. These are not the only choices. Also, that cryptographic problem from the 80s that was invented in the 70s is a choice, and that's the data encryption standard hardened by the NSA from the 70s. Yeah, and that was up until very recently a legitimate choice for new SIM cards. And if you give people a choice of store a lot of data in your databases or a little bit, too many make the choice of a little bit. So my understanding is that pretty much every operator in the world started off with shipping desk keys on their SIM cards. Now this is 10 years ago where these Java environments were first deployed to the SIM card. And many operators have since, some more recently, some early on, switched to triple dash. Virtually nobody has switched to AES. But so even those operators who have switched, of course, have only done so for newer cards that they're giving out. And older cards may still carry the data encryption standard. We estimate this, and this is a very conservative estimate, at about half of the world's SIM card still using at least one key set of the data encryption standard, of this 70s era encryption. Right? So multiply that by 7 billion cards in active use, and you see the magnitude of what this problem could be. Adding in, though, well, let me perhaps add one more thought here. This would now allow attacks that are somewhat conceivable, but perhaps not very practical. A possible attack scenario where if you know somebody is using DES, is you would capture communication between the OTA server and the SIM card. Right? This is all over GSM, or a lot of it is over GSM. So we know from a few years back how to read that. And then brute force through all possible DES keys. You'll find the one that matches, and you can use that to sign the next message as if it came from the server. Right? So that's limiting in two ways. The first way is that you'll have to hang around and wait for the network actually to send a message like that. That may be more common, around airports, for instance, where people update their roaming lists. But still, you get kind of a very random sampling of possible victims. Secondly, the cracking of DES keys has been shown over and over again to be possible, but usually at steep price points. The deep crack was probably the first public version of a DES cracker. It cost $1 million. Right? So that may not be worthwhile spending $1 million to then crack DES keys. So we'd like to improve this attack in these two ways of making it more controlled in terms of response and also cheaper to crack. And let's solve the first problem first here. We need a way of triggering the response from the card that gives us enough information to crack a secret key, and instead of just waiting for the network to send a response. There's a gap in the definition of these cards that allows us to, for some cards, get exactly that plaintext signature pair. And the gap is, how do you respond to a falsely signed command? Everybody can send a command and everybody can falsely sign it, right? The difficulty is in correctly signing it. So you can just pick a random phone number, you send a binary SMS to it, and it will do the security check on it, and it will understand the signature is wrong. And some cards ignore you. Others, though, are nice enough to tell you that the signature was wrong and that you should try again. And a subgroup of those include a signature on that error message. This one, of course, using the correct key. And since this is not just using symmetric crypto, but also the same key in both directions, so kind of key symmetry, this is exactly the key you'd like to crack to then communicate in the other direction towards the card correctly this time around. Right? Everybody understood this so far? Right? So you send something wrong to the card, and it responds by telling you that you did something wrong, but signs it with a DES key. Right? Okay, on to the second challenge. Yeah?
Are you saying that the SIM card has the same private key that the OTA server has?
So the question is, does the SIM card use the same key as the OTA server? And that is in fact the case. So every communication channel is secured by one key only, and all messages sent in both directions using the same key. Right? Terrible choice, but probably it was a trade-off. Storage on the SIM card. Do we store two keys, or is one enough? And it chose one. Thanks for the question. Good remark. On to the second problem. We don't want to spend $1 million for deep crack. Neither do we want to break it over a long period of time. In fact, the $1 million have come down to roughly 50,000 euros, so $70,000 or something, that you can buy in Germany in an FPGA cluster. It still takes one day, though. Not very attractive, I would imagine, to anybody wanting to crack SIM cards at large. However, if we had a possibility of predicting what goes into the signature, right? We can pre-compute the signature for all possible keys. Very similar to research we did a while ago on A51, another encryption cipher used in phones, which allows for rainbow tables. So let's look at whether or not we can actually predict everything that goes into these messages. Here are the packets as they're being exchanged. As I said, there's a few header fields that you have to set for the message to be sent directly to the phone, and most every phone honors this. So they will only forward messages with exactly these settings. We'll get back to this later when we talk about countermeasures. Then other significant choices for the attacker are that they say we're not doing encryption. Now this is by network. Some networks enforce encryption, some don't, but this is the most popular choice. No encryption, but signature, cryptographic checksum in the SIM card jargon. And the request not only says what it is secured by, it also specifies what the answer should be secured by, right? So it says also, you please do not encrypt your response, but sign it and send it no matter what, even in an error case. So this is the place where some SIM cards honor this, some not. So you choose the key that's to be used. So you actually have to go through a whole number of keys in probing a card. So if you know which key is affected, one SMS may be enough. But when you're first probing a new operator, let's say, you go through a whole number of choices for both the key ID and the application ID. And then you include the cryptographic signature, but it's wrong. So you just put random data in there. The response includes some of the same values. It again has a header that indicates it's a binary SMS. It includes, again, the same application ID you specified. It includes a counter. This is meant as a security measure too, against replay attack. However, luckily for this result, or unfortunate for the now vulnerable SIM card, the count is only checked after the signature is being checked. So you can throw in any counter, it will respond with an error code saying the signature was wrong and never even looked at the counter. So I'll just copy the counter you gave it and accepting it as correct, at least for this error message. And the rest is really predictable too. This is the response that says the signature was wrong in all of this. So all the fields, 1, 2, 3, 4, 5, that go into the cryptographic checksum are either attacker controlled or fully predictable. And that then makes rainbow tables possible. If you know what somebody's going to sign, which packet, you can pre-compute it for all possible key choices, right? And that's exactly what we did. And just to recap, again, much more explanation of this in our A51 research from a few years ago. What is a rainbow table? It builds up on the idea of a code book. So a large data set where you have all public and secret choices matched up with one another. For instance, the phone book would be a code book. If you consider the mapping from a name to a phone number to be a secret operation, think of it almost like an encryption function. It's easy to go one way, but it's pretty hard to go the other way without the phone book. Computing a phone book, though, for 2 to the 56 entries, Google can do it with petabytes in hard disk space. I can't do it. So we need some way of compressing this gigantic phone book. And the way we do this is by creating a data set that's not just computing one link, like the phone book does, but many links. So each of these Ks is a des function. And you keep computing them, and not just 3 times like on this slide. I think our choice is 32,000. And of these 32,000 chain links, you only keep the first and the last in this data set. So now you may cover the exact same number of values as in the phone book, but you need 30,000, or I guess 2 30,000 of the storage only. So this is becoming terabytes then, much more manageable for home hard disks. Now, if we do find a public value and you want to create a secret value from it, the lookup goes as follows. Let's say the public value, the signature we see is this 2F06. We didn't store this, right? We only stored the first column and the last column. So we look it up in the last column, don't find it. Instead of giving up now, though, we compute the des function on it, kind of working our way backwards in this chain. So we compute the des function, look it up. Again, don't find it. We compute the des function on it twice. We find it somewhere in the data set, and we know what chain it belongs to, and that chain also, one link before, has the secret item. So with 32,000 operations, DES operations, you find the secret key. Now, there's some more complexity that actually makes this rainbow, where all the DES functions are different, and where the computing time actually becomes quadratic. But I'm not going to go into this detail. Just for you to keep in mind, it's not just 32,000 operations, it's the square of that, and that makes it something like 1 minute on a computer, right? So we trade time for space. We had an attack with petabytes of storage that uses 0 time, basically one database lookup, and now we have an attack that takes an entire minute, much longer, but still acceptably long, but only takes terabytes, right? And that's possible because this protocol was designed with too little randomness, right? You prevent these types of attacks through throwing in random numbers from every direction. All right, so wait, let me pause this for a second. So at this point, I was going to demonstrate exactly how we send the messages using this phone, the binary messages, and then get the responses, and then cracking the keys. Now I'll talk at the end a lot about the responsible disclosure aspects of this. But long story short, we had a couple of different sets of SIM cards we were going to use for this demo, and one after another, the networks put in filters or even updated their SIM cards. So one after another, we lost from this demo set, which may be unfortunate for you today, but it's extremely rewarding for me as a researcher to know that even before we publicly demonstrated this for the first time, a lot of networks, these mostly being European networks, have already patched away this vulnerability, at least in the most obvious way of remotely sending SMSs. We did, just because we kind of knew this may happen, and we were this close to them months ago, recorded a video of what it did happen. In fact, a news website in Germany did. So let me just show you this first part of the attack as a video then. We had a little tool that takes a database full of phone numbers and then sends text messages to all these phones. Binary SMS, so not every phone uses that, but this Motorola phone can be reprogrammed to send binary SMS, and then the victim shouldn't show any attack signs, except for when it's an Android phone. It does very briefly say sending, but nothing more. So this was not user triggered or anything, and it does reply with a signature. And that signature now, this is the second part of the demo, that we can still crack. And I'm sure that there's plenty of networks out there still where the first part would also work, just not the ones that we were prepared to show. All right, so you get back signatures, cryptographic signatures, right? 64 bits. That's the block size of DES, and a key cracker, for which you have to specify which error code it was. We'll find this hopefully quickly. Let's see. Oops. Yeah. Okay. All right. This is running on just a single computer with, I believe at this point, 6 terabytes of hard disk, but 3 different rainbow tables, so each of them is only 2 terabytes actually. And it uses 1 GPU. This should be switching to cracking. Let's refresh here. So it uses one big GPU, kind of the exact same setup we already used for the A51 rainbow tables. Yeah, not sure what's happening with the scheduler here. So let's come back to this a little later. So the secret key that we would get from this, or that hopefully we will get from this, that is the exact same key as per your question earlier. That's now used to respond in the other direction with signed messages that encode valid Java. Right? So this should be of great concern for every network that wants to protect the SIM cards from attack. Some networks, though, kind of shrug it off a little bit too quickly for my taste, and they said we're not affected by this research at all. And they gave different reasons. Some of them said we're using encryption instead of signatures. Now, if you encrypt something that is known, with a known function, DES in this case, of course, one can build equally easily a rainbow table. Even if you use both encryption and signatures, 2 rainbow tables can crack those 2 independent keys. So encryption is certainly no cure here. And the networks that made sure that that their cards didn't give out any signatures, for instance. This is considered a bug at this point, and in fact, the standards were rewritten for cards to not give out anymore. They may still give out encrypted error messages and only enforce the encryption and not the signatures. So a whole lot more networks may be affected than they think. Some networks think they don't use OTA, so they're not affected. Some of them don't even know their own keys, but the keys are on the cards, and they can be cracked, and they can be abused. In fact, I think it's more likely that if a network operator has no recollection of what kind of keys they put in a few years ago, that those will be DES keys, because this is a very active choice that you say, I now want to upgrade to triple DES for all my new cards, and those networks that haven't done so, they're in a bad position. Now, the third one on this slide is the most interesting, probably. Some operators say, it's actually one of the 2 American GSM operators that said, we didn't even look at this research, we are not affected, we use triple DES. Now, triple DES is necessary, but not sufficient to prevent this type of an attack. There's still at least 3 ways to screwing up the triple DES secured card. The first is when they upgrade the cards, but not the OTA database column to be wider, to keep more key material. They still have just a 56-bit key, but they put it in a triple DES operation. Either they pad it with something static, or more commonly, they use several copies of the same key, right? Which in 2-key triple DES actually means that they're doing something different then, right? They run through an encrypt and a decrypt with 2 different keys. However, in 3-key triple DES, if you use the same key 3 times, encrypt, decrypt, encrypt, you're completely canceling it out. So then that reverts to single DES and actually is crackable with the exact same rainbow tables we already computed. Some operators never bother to change the keys. They say triple DES is uncrackable. Why not use 0A, 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 0A as our key for all cards, right? Because that's the programming key, right? Who would ever be able to guess that? And then some cards, this is now not by operator, this is by card manufacturer, are affected by what I want to call a downgrade attack. And downgrade attack abuses, again, kind of a gap in the specification that's not so super clear on how cards should do this error handling. And the downgrade attack abuses the behavior of the card, where if you ask it to use a certain security mechanism and it responds, no, I'm not going to do this, it will use it, though, to sign the no, I'm not going to do this. So it's a little bit contradicting itself. And an attack on, let's say, a 3-key triple DES key then would look as follows. You send a single DES signed command and request that the card responds single DES signed, and it does so. And from this, you can crack a single DES key that happens to be, because of the memory management, the first third of the 3-key DES key. That's how this particular card seems to do it. Now, this single DES key doesn't actually help you send anything to the card sign, because on the signature check, it will make sure it's triple DES. That's its configuration. Just on these error messages, that doesn't seem to be the same check. Now, you know the first half of a 2-key, 3-DES key. You send another command. It signs it with the whole 112-bit entropy key, of which you already know half. So this simplifies into a problem of, again, breaking 56 bits. Right? Same problem that you already solved before. This time, unfortunately, no rainbow table use possible, so this is a little bit more effort, brute forcing. And you do it one more time. If there is, in fact, 3-key triple DES, 2-key triple DES is also very popular. So some SIM cards, I have to emphasize this, some SIM cards give away a full triple DES key through 3 iterations of a brute force attack, or 1 rainbow table, 2 brute force, right? And I hope this will inspire some operators to look a little closer into the exact vulnerability before saying we are not affected at all. Let's check back with our cracking. Yes, we didn't actually see how long it took, but it's usually between 1 and 3 minutes on this machine, and it did find a 56-bit DES key, right? Just one of many keys of this card. Our rainbow tables are not computed to 100% anyway, though, so it helps that the card signs different error messages and from different key sets to get closer to 100% cracking. In a nutshell, the vulnerability to OTA key cracking is only there if the card does respond with something other than zero byte signature, and actually includes real data in the signature. Some cards put all zeros in it, and it's only valuable if either the DES crack works right away, either because it is just DES, or because somebody put 3 same keys in a triple DES operation, or because a downgrade attack works. If not all of these are true at the same time, then this particular attack does not work. Now, even though there seem to be a lot of conditions here, again, very conservatively estimating, 750 million cards are affected by this, where all these bad configuration and implementation choices come together. Right? So that's how you crack a key of deploying something onto a SIM card. And what would be, and now of course the question arises, what are you going to do with a Java application on a SIM card? And there's a bunch of APIs that the SIM card exposes for Java applications to use. That's the left side of this slide. And some are kind of obvious, you know exactly why they're there, like sending SMS. That's how Java applets communicate with the application provider, service provider. Some others, it's less clear why they would be there, but the mere fact that they are there makes them abusable, like dialing phone numbers. I can't think of a scenario where my SIM card should dial phone numbers on my behalf and then even type in DTMF tones, but it's of course perfect for voicemail abuse. You can log into somebody's voicemail, forward messages, all that stuff. USSD is another communication possibility. You all know USSD is like the asterisk 100 hash, these short codes. This is, it looks like dialing phone numbers, but it's actually a different protocol, and SIM cards are allowed to do that. In fact, there's payment schemes built around USSD because it's more reliable than SMS. Again, what can you do from an attacker perspective? You can, for instance, change the forwarding settings, right? Like reconfigure the voicemail number, stuff like that. The SIM card is allowed to query for the GPS location, right? Again, something I see no legitimate use for, but it's standardized and a lot of phones implement it. And so through deploying of this SIM virus, now somebody could keep querying your location and get your current location via SMS. And then perhaps the most scary and the one that I've never seen in use is the SIM card can ask the phone to open a URL in the browser. Right? And of course, that allows basically any IT attack on the phone, right? So download something from an app store, spoof a banking website to do mobile banking, all the like. So there's a lot of functions that you will never have used, that you don't actually want to be there, that your network operator would never consider using, but that the attacker now can use against you. Yet other stuff on the SIM card should be better protected. There's no obvious API you can call to, for instance, read the super secret master key. It's called KI of this card. That's used from which all the other encryption keys are derived. So all the keys that are used to encrypt 2G, 3G, and 4G voice and data traffic, they all derive from one single key, 128-bit key. If you steal that, you can completely clone the SIM card. Kind of like back in the good old days, the Comp 128, 2 days of challenging the card, you read the KI. So this should be prevented, as should the other items on this slide, kind of lateral movement on the card. However, the implementation of Java on these cards does allow somebody to read those extra items as well. The Java, my understanding, does a lot of security analysis that in a lot of other languages are perhaps found in the compiler or somewhere else. So it will, for instance, verify that you're not going out of boundaries. You can try, and it will give you an error code, an exception, and so be it. And the simple cases, and now I'm talking about 2 specific Java virtual machine implementations among a whole range, but those 2 make up for 80% of the market share or something. So in those two Java VMs, those boundaries are checked in simple cases, like the one here. You have a small array and you give it a long integer as a pointer to the array. It will tell you you are out of bounds, exception. However, and unfortunately can't disclose the exact way of doing this. It's kind of still a responsible disclosure issue. If you ask the SIM card a little bit less straightforward to give you some memory that isn't in the array, let's say through a number of dereferentizations that then result into an integer, then after all this dereferencing, somehow the card forgets to do the boundary check. And you get full read and write access to the entire memory. And this is not just to the Java process, this is to the entire smart card. The smart card doesn't really have a process concept beyond the Java SIM boxes. Right? So with this now, again, on a majority of SIM cards, this bug is found, you can read all the data that's on the card. This master KI key, you can read the payment tokens that are very popular in Africa, for instance, for mobile banking. You could be reading an NFC credit card if they were to deploy them anytime soon. And this now, and this brings me to the final part of the demo, allows you to fully clone the SIM card, among other things. So let me show you this. So I have a phone here with no SIM card in it, right? Again, it's this Motorola phone. I love this device. It's the only one that we can really fully program. And I'm going to connect this to this computer. Most of the Osmocom software actually runs on the computer and not on the phone. So the phone is kind of dumbed down to just accept whatever commands come from the computer. And I'm going to start this as a phone using a KI key that we stole from one of the SIM cards. Right? So let's see. So it's now basically a software implementation of all those functions in a SIM card. The Comp 128 in this case, I think version 2, then the KI and everything else that's needed to spoof the SIM card. Should be registering to one of the 2 GSM networks here. It picks them kind of randomly. This card is a European card, so it's allowed to roam on both. The GSMA did put pressure on the two GSM operators here to put in some extra filtering rules, as I learned yesterday. That's why the first part of the demo probably didn't work at all. I'm hoping that they did the filtering rules for the whole country and not just Las Vegas, but you never know. There should be good mobile reception here, right? So my other phone has full reception. Actually retry this one more time to make sure that the Osmocom software didn't crash or anything. It's not so super reliable. Now, back in the day, when SIM cloning was an issue, just to contrast it with this attack, people would take a card and then have 2 copies of the card a day later or so, and that was considered an issue. I'm not sure what exactly the type of fraud is that you'll do with 2 copies of your own card, but back then that was huge. Now we can do it remotely, fully remotely, and to thousands in parallel. And of course, this is an order of magnitude of SIM vulnerability that has never really been there. And there was no other research anywhere in between that ever questioned the security of SIM cards. So the response, and we'll talk about this next, from industry has been extremely strong, but fortunately very constructive too. I don't know why this is not registering. It did definitely work. Oh, no, it did. Let's wait just a minute or another minute or so. Yeah. So now it's actually registering, where before it was just kind of searching for a network that it can register with. So now it's doing what's called a location update. So that already requires knowledge of the secret KI. In fact, of the KC. That's a derivative of it that the soft SIM does. So the response from the mobile operators was extremely strong and constructive. And after having done mobile security research and actually come up with what I think are significant results for a few years now, we've never had that type of response. And I want to specifically talk about this as soon as this is working. Well, let's come back to it at the very end. I'm sorry that this is taking so long. So just to wrap up what an attack could look like. You start with a range of phone numbers, either guessed or collected in some other way, and you send binary text messages to a bunch of them, right? Tens of thousands if you want. There's definitely SMS spamming operations going on that cover millions of devices. So from those, from about a quarter, you'll get back signatures, and of those, about half would be death signatures, depending on countries. Some countries only have death signatures up until today. Others upgraded a long time ago would be less affected. But as an average, half of the ones that do respond would carry a death signature. You crack the death signature using these rainbow tables, either just the signature key or also the encryption key, and then you send a virus onto the phone. That virus can do lateral movement on the card through the sandbox escape and then steal everything. The KI, the banking application, start sending SMS, start tracking your location, basically doing everything that the virus would want to do on your phone, except for, of course, access the data on your phone. This has nothing to do with Android, iPhone, and so forth. Just going back, so okay, it's connected to Singular. You see how old this software is? So it's using a very old list of operators. Okay, so I should again use my phone number. No prank calls during the night, please. Photo boost, and this should be calling this phone in just a second. Let's see. Call is alerting. Did I miss? Oh yeah, okay. Here we go. Let me hide that phone number so that I don't switch that off once again. We lost so many through this research. So I'm being called by one of the SIM cards that we cracked right now, right? And that's basically game over for SIM card security. If you can do full SIM cloning, including this KI key, and remotely so, to what's hopefully fewer and fewer cards, but definitely when we came out with this research, hundreds of millions of cards in many countries worldwide. Thank you. Thank you. Now, as I already started telling, the industry response was strong and constructive, and here's a few things that either they came up with, or we came up with, or we kind of all came up with together, that an operator can do. The obvious short-term measure that doesn't really require too much effort is filter these types of messages. They're very specifically formatted messages. You saw the header values indicate that these are binary text messages, and the only sender and or recipient of a binary SMS should be the OTA server. So two phones should never be exchanging binary SMS. So just putting in a filtering rule that says do not let through binary SMS unless it's from our OTA server, that's a good first approximation security. A lot of networks, especially this past week, as they raced to implement them before this demo, overdid it a little bit. They forgot, for instance, that roaming users in their network, of course, want to talk to their OTA server, right? So a lot of roaming optimization didn't work anymore. Also, for instance, Apple FaceTime, that uses a specific type of SMS to initiate the connection. That stopped working in a couple of places. So figuring out the exact filtering rules you need, that may be a little bit more difficult. Some testing work, some measuring what traffic you actually have in your network. But it's still, I think, the quickest short-term measure to at least make us not able to present or demo this, and probably makes it much more difficult to abuse too. On the same level of difficulty, without much consideration, is deactivating OTA altogether. This OTA functionality, as I said, in a lot of networks isn't even used. They sometimes even forgot their keys. So deactivating it may not be a bad choice, especially if this real estate for older cards is burned now anyway, and Visa, MasterCard are not going to allow the NFC tokens onto your card anyway. Only on newer cards they would. Then why not just switch it off, right? Now, in that same direction, but a little bit more smartly, you can reconfigure cards to basically upgrade them from single desk to triple desk. And this, I want to go into the details here because this is probably my favorite part of this entire story. The standard says you're not supposed to and you're not allowed to. The standard specifically says you cannot change security configuration. Probably the people were thinking to prevent types of downgrade attack where you make it less secure. But this also prevents upgrade attacks, right? What some SIM vendors or some operators with SIM vendors now came up with, I love it. So they take the Java exploit we have, deploy a Java applet onto the SIM card, hack into their own card, rewrite parts of the operating system to allow these types of upgrades, and then upgrade to triple desk. Right? How is that for adapting hacker mindset in industry, right? I love it. So not possible on all cards. In fact, some are so secure that they don't even have Java bugs, so they need to replace their cards. Too bad. So only when you have 2 bugs you get to fix one. If you only have the worst one, then you're stuck with it. While in the card and while hacking your own cards, it would also be nice to prevent them from giving out signatures, but that's more than just a configuration setting. That actually rewrites some logic, so I don't think anybody is doing it quite yet, has quite figured out what all has to change for them to not disclose crackable ciphertext anymore. That helps us break these keys so much faster. Now, hopefully in the midterm, most networks will have done both filtering and upgrading the OTA keys. Where that's not the case, I would imagine that that phone manufacturers want to jump in with something like an OTA firewall. I think it's pretty shocking that that all this communication goes on with absolutely no way for the user to opt in or opt out. And that functionality really has to be brought back. Very, very old Nokia phones, like the Nokia, I think 1110, that still asks the user, is the SIM card allowed to now send a text message? Newer phones don't do this anymore. Why? I don't know. I think we should get that control back, at least on a low, nerdy kind of a rooted Android type level as a supplementary security measure. A few more words on the responsible disclosure. I don't usually talk about it so much because it's kind of falling into the same pattern where we disclose something, then industry pronounces strongly how this is infeasible or only with very specific tools, or only affecting a few devices. None of this happened this time. Everybody responded to the criticism by trying to upgrade it. And in fact, not just everybody individually, but the different operators helped each other with ideas and helped their SIM vendors who are a little bit lagging behind in understanding these attacks, some of them anyway. Helped them all understand how to, best practice upgrade this, and shared all this through the GSMA, is the organization that facilitates the exchange. An environment that I've never experienced in terms of responsible disclosure, which may be due to just the general sentiment right now of, you don't want to be responsible for being the one enabling surveillance and other types of criminal activity. It may also be, though, that it's just this time we didn't only break the privacy of all their users, we also added in a little bit of revenue loss element, and that got them running. So maybe as a recommendation for other researchers, don't just try to protect the user, try also to hurt the operator, and then they'll be much more focused on it. Three more recommendations here on the right-hand side. I won't go through them, just kind of for reference if you ever want to disclose. I think the important ones are be in control of the process, right? Like choose the partners you want to disclose to wisely, and make sure it's no lawyers, that there's no NDAs in the ways, that it's really a constructive environment where they know you set them a deadline and you gave them sufficient time to fix it, but no more than that, right? All right. So I hope this was at least a little bit inspirational, even though it's kind of an already fixed vulnerability for some parts of the world anyway. But I hope, I foresee this being the first result in SIM card hacking, not the last. There's plenty of applications that are running on SIM cards that could have implementation bugs. There's plenty more in the Java world to be found, and there's probably stupid configuration key choices that we didn't even think of yet. And if you do find any such bugs in the future, perhaps this was also encouraging to go a responsible disclosure way and actually making change happen instead of just criticism, what I kind of got frustratingly used to as a security researcher. Criticism of industry not moving. This time they did move, and I'm thankful for this, and thank you for your attention. Any questions? So the question is, can you test for these vulnerabilities remotely? And you can certainly test for whether the cards give out crackable ciphertexts remotely. That's just a binary SMS, sending and receiving one. You can't actually test whether this is DES or not without having the rainbow tables, because they look the same from the outside, right? So only when you cracked it, you know that it was DES. You don't never know the other way, right? Question here?
Is there a chance that we re-enable the auto
So very, very good question. Is a way of knowing which applications are already on your card and seeing how the operators enable or disable it? Unfortunately not. Usually you have no way of seeing this communication, and you have no way of peeking into the SIM card to see what's stored on it. If you suspect your phone to receive an OTA upgrade soon, you can use a SIM spy, like SIM trace, for instance, to be like a proxy between the SIM card and the phone, and then you'd see the packages. But those may be encrypted, may just be signed. So it's kind of a little bit of luck trying to find this, and I think the operator would be the only ones really be able to tell what you have and how it's communicating, unfortunately. So big gray area, and I'm strongly calling for phones to give control to the users back, over which messages are being exchanged and who receives them. Thanks. Any other questions? Yeah, go ahead. Sorry. Oh, yeah. So let me go back to this slide and emphasize this point a little bit more. You see how I say this is only half effective? Because the filter really only helps when your user is in your network. It doesn't help, for instance, when the user is in another network roaming, unless you do home routing, which researchers have been called for at least 6 years or so for privacy reasons. Now they may actually do it to prevent these SIM vulnerabilities. But let's say, even with home routing, and this is now coming to your question, a fake base station that completely emulates the network, of course, is still allowed to talk freely to the SIM card. So filtering, very good first approximation. That keeps me away from demoing it, but definitely no long-term solution. IMSI catchers are already widely deployed, and this would just be one more abuse scenario. And in fact, if you think about it, an IMSI catcher has to crack all these keys, the KCs, the session keys, on the fly, and it may miss it sometime. If they get to crack the KI, they're worry-free. They pre-compute all the keys they need, right? So definitely abuse there. And the last possibility, of course, if you have a malware on your phone, that can speak to the SIM card with no network level filtering whatsoever. Right? Any last question? Go ahead. Good question. Do the JVM vulnerabilities affect other users of smart cards too? So this is a smart card, of course, but the operating systems that SIM cards use are pretty custom. So I don't think that those vulnerabilities will be found in any other use of smart cards. But you never know. Maybe a smaller use kind of recycles them. So this is all the area of Java cards, but everybody implements their own Java card. Let's say the most common one, I think, would be Jacob card by NXP. That's not used as a SIM card. So the SIM card manufacturers create their own Java card implementations, and those all seem vulnerable. But if that question was kind of motivated by your desire to research this further, we are no Java experts whatsoever, and we found these bugs in very short time. They're very obvious bugs. If you compare them to what kind of bugs are found in kind of PC implementations of Java, there's worlds in between. And so I think there would be hundreds of Java bugs in SIM cards, of which we just found the tip of an iceberg. Right? So definitely encouragement for anybody to look at it stronger. Yeah. Okay. Well, thanks again. Growing every day. So these would be a very attractive hacker target, and we looked at how to hack them and found surprising things. SIM cards were originally meant as a way for the phone to be paired with a contract, so that the charges would be put on the right contract, and then the calls would reach the right phone number. But they've been extended into all kinds of other directions since. With functions for very feature-limited phones, like storing an address book or storing text messages. These are the more known extensions of SIM cards, but also through custom Java code that can pretty much do anything. and that can be updated at any point in time. Popular uses here are roaming management. That is, when you touch down in a country that you haven't been before, your operator updates a list on your SIM card that says, I prefer this network over this other because I negotiated better rates. So it has to do with revenue optimization. Also, payment applications are found on SIM. Remember that? So that's a different type of research, and that abuses just one application of the SIM card. We want to go deeper, but not quite as deep as the smart card. So that's also something we're not going to discuss today. If you go back, I think 2 years ago, I gave a talk here with Karsten Nohl. There we show how to break a smart card. But who remembers the talk from back then? It was a somewhat elaborate process that took a couple of days in a lab. So maybe nothing you would do to your neighbor's SIM card just to break it. In fact, you would physically need to break it in order to break into it. So that's also not of concern. Instead, we want to focus on the management interfaces that network operators use to deploy or reconfigure Java applets to on the SIM card. And we first want to look at the management interfaces for the communication of those Java downloads, and then look at what the Java applet is allowed and should not be allowed, can do anyway on the SIM card. Sounds good? Yeah? Okay. If there's any immediate question or any questions, raise your hand, right? I'll try to answer them as they come along, otherwise at the end. So we cards in the developing world a lot already, in Africa predominantly, I take it, but it's also coming to the developed world in the form of NFC payment tokens. So when your phone becomes a credit card, that's facilitated through a software download onto the phone. Very popular in Japan, as I learned today already. It's coming here, any day now, but they've been saying that for years too. We find a bunch of different security mechanisms on the SIM card. It's a complex computing system, so it has to secure a whole range of different things. And let me first state what we're not going to cover today, just to make sure what the focus is. We're not discussing, how to break PIN numbers that used to lock SIM cards. In fact, the attacks I'm going to present, they were completely outside of the realm that's even protected by PIN numbers. So you can send those messages that we'll be using to cards where you don't even know the PIN number or it has not been typed in. We're not going to get into authentication functions. What used to be SIM cloning some 8 years ago, COMP 128, some people may remember. We want to go into two deep dives here. One, to discuss how somebody would be able to deploy a malicious piece of software onto the SIM card, cracking some cryptographic keys with permissions to do that. And then we want to discuss what one can then do with that Java on the SIM card. This is all grounded in these management protocols I mentioned earlier that are meant for the operator to control the SIM card while after they already gave it to the customer. And the communication between the operator and the SIM card is all text messages, but of a certain type that is not actually displayed on the user phone, but instead directly forwarded onto the SIM card. So there's a header in every text message that defines its type, and certain types are supposed to be shown to the user, others go directly to the SIM card. And virtually every phone honors these flags. We found maybe one phone in the last 3 years that just ignores OTA entirely. And so to secure this communication.
This is track 6. One more time. This is routing SIM cards with Karsten Nohl. The other talk has actually been moved to tomorrow, Thursday, at 15:30. So please welcome to stage Karsten Nohl.
Thank you very much. I'm a security researcher out of Berlin, where I run a hacking think tank. Our research mission is to find vulnerable cryptography in everyday use. And we've been doing this for a few years, and we found applications on and on from 20, 30 years back that are still being used, and of course they're using bad encryption. Now we thought we were done until we found this one more application. Maybe it's the last one that falls into our research. We never know. But I'm here to speak about SIM cards, the little computers in your phones, or in most everybody's phones. There's a few exceptions of older CDMA phones that don't use SIM cards. Everybody else uses a phone. GSMA says there's 7 billion in active use